Hello everybody, and welcome to our video on vector functions and space curves. So essentially what we're going to be talking about now is functions that not only take inputs perhaps of vectors or individual variables, but also output vectors. So this is a function whose domain is the set of real numbers and whose range is a set of vectors. So here we've got this notation, r of t equals angle bracket f of t, g of t, h of t, angle bracket f of t I plus g of t j plus h of t k. So generally speaking, when we're talking about vector functions, we often use the variable t because a lot of applications use time as the variable when you're talking about vectors. So with that in mind, we call f of t, g of t, and h of t the component functions of r of t. All right, so fact, if r of t equals this vector function expression, then the limit as t goes to a of r of t is equal to the vector that results from taking the limit on each component. So that's not hard to show using the definition of a limit on a vector. But we're going to go ahead and just take that as a given here. So let's go ahead and calculate this limit. So this should be the limit as t goes to 1. Well, actually, that's fine. We'll just write this now, and then we'll kind of recondense everything, do some work off to the side. All right, so in order to keep this kind of organized, let's just split our work up here, and let's take each of these limits individually over here. So if we want this limit as t goes to 1 of t squared minus t over t minus 1, I'm going to need to factor my numerator. T minus 1 times t over t minus 1. Those factors cancel, and now I can take the limit by just plugging in t equals 1, which gives me 1. Now, if I take the limit as t goes to 1 of this square root, well, the square root is continuous for positive values, so again, we can just plug in t equals 1, which gives us the square root of 9, which is 3. Now, lastly, we want to look at the limit as t goes to 1 of this sine of t, pi t divided by ln of t. Now, the first thing we have to notice here is that this function is, well, this is an indeterminate limit. So when t goes to 1, ln of t goes to 0. And this is going to sine of pi, which is also 0. So this is 0 over 0 indeterminate form. And so we can use L'Hopital's rule for this limit. This gives us pi times cosine of pi t over 1 over t. Now, both of these are perfectly continuous at t equals 1, so we can just plug in. Cosine of pi is negative 1, so this is pi times negative 1 over 1, which is 1. So this is negative pi. So altogether, our vector should look like 1i plus 3j minus pi k. Okay, that's it for that one. So now let's take a look at this curve. Describe the curve defined by the vector function. So basically, we just want to make sure that we're able to identify some common basic vector functions. And in this case, this looks like exactly what we expect for the vector function description of a line. So this is the line that passes through the point 1, 2, -1. So here we've got x naught, y naught, z naught. With direction vector, one, 5, 6. All right, so that's a pretty thorough description of the curve. Now let's go ahead and move on to another example. So here we're going to sketch a curve whose vector equation is given by cosine of ti plus sine of tj plus tk. Now, this one's a little bit challenging because we can't really realistically plot all the points of a vector equation, right? We might plot a few points, but this is going to be in 3 dimensions, so it would be really cumbersome to plot more than a couple points. But B, it's just not super realistic. We have to instead think about how we can visualize this thing and understand what's actually happening with its components. So, well, let's take a look at a couple things we can figure out. So cosine of t has to be strictly between 1 and -1. So that tells us that the x value that we get has to be between -1 and 1. And similarly, the y value that we get has to be between 1 and -1, since sine of t is between 1 and -1. And this t, this is our component for z, this simply increases when z increases. So if t is increasing, you should expect your points on this curve to go up. So let's just take a look. Let's plot our first point. All right, we'll do that in blue, I think. So when t is 0, we get 1 and 0 and 0. So for t equals 0, r of 0 equals 0 plus 0. Or sorry, 1 plus 0 plus 0. In other words, that's just going to put us right here. So the curve that we're talking about is the curve whose points are the points touched by this vector r of t. So now if we think about what happens here when t increases, like when t goes to pi over 2, I'm just going to plot one more point here. It's not super, maybe 2 more points. So again, it's not super realistic to plot a bunch of these. Cosine will be 0. Sine will be 1, and this will be pi over 2. So here, I should be lined up with x equals 0, y equals 1, but I should be like up a little bit to pi over 2. So this curve is like coming from this plane here, and it's going up and curling around the z-axis. And so in general, what we should realize is that the x and y coordinates are forming a circle around the z-axis, and the y-coordinate here is just making the point go upwards as you go around this circle. So you can basically just draw this like a spiral up here. So again, with these sketches of curves, I really just want to see that you can convey the idea of the curve, not that you're drawing like a perfect 3-dimensional picture, right? So like here, I'm just adding this little shadow image to show that I know that this curve is basically just spiraling up over this circle. But it doesn't have to be perfect. I don't expect anyone to be artists. I just expect you to be able to draw enough to convey that you understand the idea of the behavior for a curve. Okay, so let's go ahead and move on to another example. Find a vector function that represents the curve of intersection of the cylinder x squared plus y squared equals 1 and the plane y plus z equals 2. Okay, so first let's draw our coordinate system and make sure we pretty much understand what these surfaces look like. So the cylinder here, so keep in mind that we're describing a three-dimensional surface and we only have two variables. So that means that since z isn't included, z can be any value. So that tells us that what this is describing is the set of points that make a circle around the z-axis but it should include all possible z values. So it's a cylinder. Not a great cylinder, but it's a cylinder. Let's try that one more time. Make it just a little bit better. I don't know if that's better. Whatever. Okay, so now we've got our cylinder, and we want a plane to intersect this cylinder. So y plus z equals 2. So we can rewrite this as z equals 2 minus y. So in other words, when y is equal to 0, then we should get z equals 2 for any x value. So if we think about that, 1, 2. So what we're saying here is when y equals 0, we get a line that passes through here. And this thing's going to have a slope where z decreases by 1 as y increases by 1. So this thing here is like cutting this way. And this is a plane, right? It fits our equation for a plane. So it looks something like this. Again, just want to make sure you draw enough that you're conveying the idea of what this thing is. And this should give you some intuition about what is happening here, which is that where this intersects, it's sort of slicing out an oval there, you might say. Well, this is relatively straightforward, actually, to do. So first what we want to do is find a vector representation. Well, the only thing we want to do is find a vector representation of this red curve. But what do we know about this curve, actually? So we know that x squared plus y squared is 1. So that tells us the x and y components on this curve actually have to satisfy that x equals cosine of t and y equals sine of t. Now, of course, there are many parameterizations we could use here, but this one works perfectly fine, right? Because we get cosine squared plus sine squared equals 1, which is true. And that describes cosine and sine for x and y describe exactly what we want, which is an image of a circle on the xy plane. So now we just need to deal with z, but that's pretty easy because z is equal to 2 minus y, so z is equal to 2 minus sine of t. So x, y, z is the vector cosine of t, sine of t, and 2 minus sine of t. Now, of course, as always, there are many parameterizations for these vector function curves, but one of the things we notice about this parameterization is that when t equals 0, that starts us at 1, 0, and 2. So the coordinate corresponding to t equals 0 is basically this point. And then as t increases, this curls around this way. Okay, well, that's it for example 4. So let's go ahead and move on. So here, we're just going to take a look at a graph of a function that I think is kind of interesting, and it'll come up a lot in different examples. This is called the twisted cubic. So r of t equals t squared, t cubed. So this is what that looks like. It's got this twist in it. And this function is a really good example, I think, of showing sort of how these components interact. So let's look, for example, at what happens if I try to reparameterize this expression. So imagine that we just fixed some z value, and we just looked at the relationship between x and y. So x equals t, and y equals t squared, so y is equal to x squared. So if we take this curve, and let's see, x will be our red axis here. So like this, it's hard to get these things perfectly lined up straight. And my curve doesn't go on forever in each direction, so it's not perfect. Well, hopefully that's close enough that you can see that if you look overhead, like you're ignoring the z values here, and you're just looking at the relationship between x and y, you get a quadratic function here. Now, let's take a look at the relationship between z and x. So in this case, z would actually be t cubed. So this is what we get when we ignore what's happening to y. So we want to spin this around and not look at what's happening to y. Actually, I want to go this way. Here we go. And so what do we see? We get the curve of a cubic function. So when we ignore the y-axis and we just look at the relationship between x and z, we get this cubic curl. Now, another thing you could see is that z is actually equal to, so this would be y is t squared. So if we want 3, it would be y to the 3/2. Now, that's not a function that you see quite as often, but nonetheless, if we, well, if we can get the model to let me click on it again. Come on. There we go. So if we ignore the x-axis, this is what that function looks like. So hopefully that helps you visualize how these things interact. And it's definitely one of the helpful things for getting a view of what these functions look like in general, is if you can or I should say, remove the parameter between variables and ignore one of your components, lets you get an idea of what like the image along one of the planes is. And when you see how those interact, you can kind of see how it builds all together to create something like this twisted cubic function. Okay, so let's move on to a definition. So this is the definition r prime of a vector function r. The derivative r prime of a vector function r is defined as dr dt equals the limit as h goes to 0 of r of t plus h minus r of t divided by h. So this is extremely similar to the standard derivative definition that you're used to from Calculus 1. Let's just take a look here and see what this means in the context of vectors. So here we've got a curve that's r, and we've got it in purple here. So this green arrow here, this green line, is actually the vector that's corresponding to our tangent vector. So that essentially means that the derivative is describing the direction of this vector, right? So this is our tangent vector here. Derivative tells us which direction that tangent vector is going. And if we take a look at these components, so what does each part of this represent? So here, this black vector here is r of t plus h, and this black vector is r of t. So h is the difference in the value of t and the parameter value, which decides how far you've moved along the curve to get from one vector to another, from the end of one vector to another. So when I subtract those two vectors, well, what do I get? I just get this red vector here. So that's just the difference between the vectors r of t plus h and r of t. And so when we divide this by h, that essentially normalizes it in terms of the parameter, right? So you're asking what this difference is, and then you're dividing it by the change in the parameter. And so when we take this limit, we're seeing what happens as this parameter change goes to 0. And that tells us what this slope of this line looks like as you get arbitrarily close to just this final point here. So that's the basic idea. Hopefully that makes some sense there. All right, so definition: the tangent line to the curve at point P is defined to be the line through P parallel to the tangent vector r prime of t. So this is the same standard kind of definition that we deal with in 2 dimensions, just extended to 3 dimensions. So if you know your point and you know the tangent vector, we can find a line just like we did with our previous vector line equations. Now, another definition that's going to come up frequently throughout the class from time to time is the unit tangent vector. So we denote this particular vector as t of t. And this is just the derivative vector divided by its magnitude. So that just gives us a vector whose length is 1 and is pointed in the same direction as r prime. So let's look at a theorem here real quick. Oh, we had some formatting issue here. Well, that's strange. Not sure how that happened. Let me try to fix that real quick. All right, sorry about that. So if f of t, g of t, h of t, the vector r, has all differentiable functions f, g, and h, then r prime of t is equal to the vector f prime, g prime, h prime. And this basically boils down to, you're taking this limit for the derivative, and we know that for limits on vectors, you can just take the limit of each individual vector component. And so that's exactly what you're going to get here. When you take that limit along each component individually, you just get f prime, g prime, and h prime. So that means that for any derivatives that we can compute directly on components, we can just do exactly that. We don't necessarily need the definition unless it's something that we don't have a simple rule to compute. So if we want r prime of t, in this case, we just take this derivative. Derivative of 1 is 0, derivative of cosine is negative sine of t, I, plus derivative of 2 is 0, derivative of sine is cosine of tj. And so if I want r prime at pi over 6, well, sine of pi over 6 is 1/2, so this is negative 1/2 I, plus cosine of pi over 6, which is the square root of 3 over 2, j. All right, so now that we've done that, let's just take a look at a few facts about derivatives and products and cross products of various vectors. So this is another thing where I'm not going to prove this, but actually I think it's a pretty straightforward proof. These proofs are pretty straightforward, and it's the kind of thing I would certainly consider putting, especially the simpler ones, on test material or quiz material. But I'm going to skip the proof for time here because this video is going to be long enough as it is. So first of all, the derivative of a sum of two vectors is equal to the sum of the derivatives. The derivative of a constant times a vector is equal to the constant times the derivative of the vector. And then the derivative of a product of a function f of t times a vector function of t is f prime of t, vector u of t, plus f of t, vector u prime of t. Now, I want to be really careful here. This is regular multiplication. This is not a vector function, so this is not a dot product or a cross product. This is a real valued function or a scalar valued function. Okay, so now if we take a look at this, now we've got the same product rule for the dot product and the cross product, and it works the same way. But this is what we have to be careful with. So when we do this dot product here, so vector u dot vector v equals vector u prime dot vector v plus vector u dot vector v, and there should be a dot there. When we take this, the order for the dot product doesn't actually matter. So you could have vu prime and v prime u for these multiplications, and that would be fine. But when we look at the cross product rule, just recall that the cross product order does matter. So here, you have to be careful with the cross product that you consistently write it based on the order of your cross product. So u prime cross v plus u cross v prime. If you change that order in either of these pairs of the products, then that's going to mess up your answer and it's not going to be correct. Now lastly, we have a chain rule for vector valued functions. So this is a vector function where your variable inside the vector is in itself another function. And this chain rule works exactly the same way you'd expect. You just get f prime of t times the derivative of the vector with f of t treated as your variable. Okay, now let's see if we can apply some of these facts to show an interesting fact here. So if the magnitude of a vector is always a constant value, c, then r prime of t is orthogonal to r of t for all t. So this might seem kind of strange to imagine, but actually there's a really simple example of something that satisfies this. So let's just draw a little picture here. What's the simplest example of something that satisfies this property? Well, that's going to be the sphere. Right, so if we draw a sphere, my sphere is not very good. Well, close enough. So if we draw a sphere, what do we see about the sphere? The definition of the sphere says that every point on the sphere is the same distance from its center. So that means if we've got a sphere centered at 0, 0, then each vector for each t that lands us on a point on the sphere. Now, of course, we're talking about curves, not surfaces, so maybe we should really be thinking of like any curve that just travels along the sphere, right? So this would be our r of t, would be some curve on the sphere. So the vector length is going to be c the whole time. It might be pointing in the opposite direction or something, but the magnitude of this is going to be c always. And what do we also see? That any tangent vector is going to be orthogonal to the curve for all t, but that should make sense because any tangent vector should be tangent to the sphere. So any point you've got on the sphere from this r of t, it should be tangent to the curve and the sphere at the same time. So hopefully graphically that kind of makes sense. But let's actually show that that is always true. So that should make sense for a curve that's on the sphere. But how do we show that that's going to be always true in general? Well, we want to show that r prime of t is orthogonal to r of t. And when do we know that something is orthogonal? So we have two theorems that we've been using for this kind of thing most of the time, which is our theorem about dot products or our theorem about cross products. So we know if the dot product of two vectors is 0, then those two vectors are orthogonal. So that's what we really want to show. We want to show that r prime of t dotted with r of t is 0. Well, what do we know? We know that the magnitude of r of t is c. And what else do we know about that? Well, we know that if the magnitude of r prime is c, we know that the magnitude squared, the magnitude of r, not r prime, the magnitude squared is the dot product of r with itself. So this would be equal to c squared. So we know that the dot product of r with itself is a constant c squared. And we want to show that the derivative r prime times r dot r is 0. Well, here's what else I know. I know that if the product of these two things, this dot product, is a constant, then that tells me that if I take the derivative with respect to t of r dot r, I should get 0. Because it's the derivative of a constant. Okay, but what else? I should also get that the derivative of r with itself is what? Well, according to our dot product rule, we get r prime dot r plus r dot r prime. And we actually know that the dot product can multiply in any order, so this is 2 times r prime dot r. But this also has to be equal to 0. So 2 times the dot product, been dropping my vector symbols. So 2 times the dot product of these vectors should be equal to 0. Well, that of course means that r prime dot r should be equal to 0 if we divide both sides by 2. So that's it. That's all we've got here for that example. Hopefully that one wasn't too tricky. Let's go ahead and move on to talk about integrals. So integrals of vector-valued functions are pretty straightforward. The way we define vector integrals is similar to our standard integral as a Riemann sum. And the immediate result that we get is that you can integrate a vector function by integrating its components individually. So just like we can split up regular integrals on sums, you can split up these vector integrals on sums. So instead of evaluating a to b of the whole vector function, you can integrate each component individually, just like we did for derivatives. Additionally, the fundamental theorem of calculus can be extended to vector functions as follows. If r is a continuous vector function and cap r, the vector cap r, is an antiderivative of vector r, then the integral from a to b of vector r of t dt equals vector r of b, vector cap r of b minus vector cap r of a. So that's the regular old fundamental theorem of calculus for definite integrals. Now here we're just going to evaluate an indefinite integral. So for this, we just break it down into its components. 2 cosine of t dt I. And remember, it's the integral times I. So first you evaluate that, plus the integral sine of t dt j, plus the integral of 2t dt k. So the integral of 2 times cosine of t is 2 times sine of t, I, plus integral of sine is negative cosine, so we can actually make this minus. So minus cosine of t, j, plus 2t squared over 2, which is just t squared, times k. All right, and that's it for example 8. Okay, so let's move on to a different kind of question. So here we've got something a little more complicated. Two particles travel along the space curves r1 of t equals t squared t cubed, and vector r2 of t equals 1 plus 2t, 1 plus 6t, and 1 plus 14t. Do the particles collide and do their paths intersect? So this is a little bit tricky because these sound like the same question, but they really aren't. So we have to figure out what makes these two questions different. So first of all, this first function is the twisted cubic that we looked at earlier. And this question is a line. So if you imagine what a vector-valued function is doing, it's assigning t values to a point on the line. And so as your t value changes, your point moves on the line. And the same thing is happening on this twisted cubic. So let's say this thing, and maybe we're looking at one of those cross sections of this twisted cubic. So maybe it just looks like this, something like this. So the question is, do these lines collide? So first of all, do the paths intersect, and do they collide? So do the particles moving collide? Well, for the particles moving to collide, they would have to be not just in the same place, but they'd have to be at the same place at the same time. That's really the key thing here. So for the particles to collide, we're asking, are the particles in the same place at the same time? So for this, this is actually pretty straightforward to check. We need to find a potential time. So let's find out when it's possible that the x components could be equal. So we'll call it x1 equals x2. So that would be t equals 1 plus 2t. So if I subtract this t and this 1, we get negative 1 equals t. And now what I'm going to do is just check if y1 and y2 are then equal. So y1 would be t squared, which would be 1, and y2 would be 1 plus 6t, which would be negative 5. So these are not equal. So no, the particles don't collide. Because the whole idea here is that all three coordinates should be equal for the same t value. So the only t value where the x coordinates are equal is this. So the only way they could collide is if the y coordinates and z coordinates were also both equal. But that's clearly not the case here, so we can move on. Okay, so do their paths intersect? Well, that's a little bit of a tougher question. So here, we need to actually take and remove the parameterization of the curves so that we don't have to worry about whether they have the same t values or not. So for the first curve, we have that x equals t, and since y is t squared, we can write y as x squared and z as x cubed. So there, we've removed the parameterization for each component. And now for R2, we've got x equals 1 plus 2t. Now we need to solve this for t, so t equals x minus 1 over 2. So that means y equals, so 1 plus 6t, so that's 1 plus 6 times x minus 1 over 2. That's 3x minus 3 plus 1. So that's 3x minus 2. And for z, we get 1 plus 14 times x minus 2 over 2, or x minus 1 over 2. Okay, 14 divided by 2 is 7. That's 7x minus 7 plus 1. So that's 7x minus 6 for z. So now we're just looking at these. We're ignoring the t parameter and just considering x as my independent variable and y and z as my dependent variables. So now we just need to consider, can we get the same y and z values for a given x value? So if y equals x squared, so I should call this maybe y1 and y2 here. So if y1 equals y2, that would imply that x squared equals 3x minus 2. So x squared minus 3x plus 2 equals 1. So that's x minus 2 times x minus 1 equals 1. So we get two potential x values, x equals 2 or x equals 1. So there's two places that we could potentially have these curves intersecting. And now we do see that the y values are the same here, right? They're definitely the same for these two x values. But now we need to check those x values for z, because if the z coordinate isn't also the same, then it doesn't matter if the y values are the same. So for x equals 2, if we check z1, we get 8. And for z2, we get, let's see, that would be 14 minus 6. That's also 8, so that's good. And if we check x equals 1, for z1, we get 1 cubed is 1. And for z2, we get 7 minus 6, which is 1. So those are equal. So that means that in both of these cases, the coordinates intersect. So we weren't asked to specify where they intersect, but we can go ahead and do that. So when x equals 1, y should be also 1, and z should be 1 as well. And when x equals 2, y should be 4, and z should be 1. So those are the points where the paths intersect. But let's be clear, the paths intersect. That doesn't mean the particles traveling along those paths collide. All right, well, that's it for this section. So thank you for sticking it out and watching the whole thing. Have a great day.